Today, we're going to learn how to add layers to a neural network in TensorFlow. Right now, we have a simple neural network that reads the MNIST data set, which consists of a series of images, and runs it through a single, fully connected layer with rectified linear activation, and uses it to make predictions. We have accuracy reporting that tells us what we're doing, as you can see. However, getting 0.6958 on MNIST is really bad. The top quality networks get around 99% accurate, and we want to try and get better. So the simplest way to do that is just to add more layers. So we're going to go to 3 fully connected layers. To do that, we first have to make sure that all of our names for our variables make sense. We should call all of them weights n and bias n. We have to define our network. So we're going to say out1, out2, and then y here. So we're going to multiply the input times our first weight matrix and then add the first bias vector. Then we're going to take the output of that, out1, and multiply by the second weight matrix and add the second bias vector. And finally, we're going to take the output of our second layer and multiply it by our remaining weight matrix and bias vector. We're going to need to change the sizes. So we'll keep our original one the same, and then the second one will go to 350, then to 350, 175, new lines in here, and finally it's going to go from 175 to 10. As you can see now, all of the dimensions align for the calculations we're doing. So you can see that the x is a 784 dimensional tensor, and we're multiplying it by a matrix that's 784 by 350, and then so forth. This should work smoothly. As you can see, the accuracy is a lot better. We added about 20% there. However, it takes a little bit longer to calculate. And once you start adding in multiple layers and getting a deeper network, that's probably about the time that you want to use some sort of GPU to do your computations on. We could go as far as we wanted with this and keep adding layers and layers and layers, but if we were to do that, you would see that the advantage wouldn't be as big. Another thing we might want to do instead is we might want to add in some sort of convolutional network. So the first thing we would want to do is we need to reshape our input. So currently our input is a 784 dimensional tensor, which is, you can think of it as a really long vector. We need that to be in the shape of a matrix. So we're going to use the reshape function. Then we'll define our layer. A lot of what we're doing here doesn't really have a lot of rhyme or reason to it. It's just kind of ad hoc. 4 layers would probably work just as well as 3, and a kernel size of 4x4 or 6x6 would work basically the same. We're trying to come up with something that seems reasonable. So the input to our convolutional layer has to be a matrix instead of a vector, and the output of our convolutional matrix is a matrix as well. Now that we've defined our convolutional layer, we're going to note that the input to a convolutional layer is a matrix, and so is the output. So we're going to need to figure out the size the output is so that we can reshape it into a vector to feed into our fully connected layers. We're going to call the reshape function in a similar way as above. But first we need to know what size the output layer is. To do that, we're going to call the getShape function, and then we'll just quit. As you can see, we now have a 24 by 24 by 3 dimensional tensor. 24 times 24 times 3 is 1728. So we're going to reshape it into a 1728 dimensional tensor. Now, this should work as we want it to. If you note, the accuracy is pretty good here, except that it makes the model a lot slower. Again, a GPU starts to get really useful once you have multiple convolutional layers. In fact, if you notice, the accuracy didn't really plateau at any point here, so we could probably add even more training epochs and we'd get a better result.